So it's only limited to ionic substances. For example, if I want to write the lattice energy, if you're given a value, delta H lattice energy of any other ionic compound like aluminium oxide, Al2O3. So the equation or the reaction whose energy change we're talking about is you're going to have aluminium ions in gaseous state and you're going to have oxygen ions in gaseous state, and they would get together to form 1 mole of solid ionic lattice, which in this case is going to be aluminium oxide, and it's going to be a solid. So this has to be 1 mole. So your aluminium ions, they need to be 2 moles, and the oxygen ions would be 3. TK, Lubena, is that clear?
Yeah.
Just similarly, one more equation. Let's say we're talking about the lattice energy of let's say MgCl2, and they're asking for the equation. Okay, whose energy change is this? What energy change does this represent? So it's going to be Mg2 plus ions in gaseous state, Cl ions in gaseous state, and these ions would be joining up to form 1 mole of solid MgCl2, which is going to be a solid. So this would be 2 Cl ions. Okay, is this clear?
Yes.
So now the value, it's always going to be exothermic because bond formation is happening. Always exothermic, always bonds getting formed. So what we're going to discuss is uh, the value of the lattice energy. Now the value of the lattice energy is, first thing is, it's kind of important that you know what the range is going to be. Delta H lattice energy is usually in this range, usually minus 1002 kilojoules per mole to minus, I mean, it's not a fixed range, but anything close to this value. So now the reason you should know this range is that it's very important that you because you'll be finding values of lattice energy a lot. So uh, I mean, if you get a value like plus 500, then you know that your answer is wrong. If you get a value like minus 25,000, then you know that the value is wrong. So if you have an idea of what your answer is going to be, in what range the answer should lie, then it would be easier to spot any wrong answers. Now, stronger the lattice, if stronger bonds are formed, stronger ionic bonds are formed, then delta H lattice energy is going to be more exothermic. Okay, Lubena, is that clear as well?
Yes, sir.
So it's going to be more exothermic. So what do you think? How do you determine whether an ionic lattice is strong or weak? Like what factors contribute to that? Any idea?
The size of the atoms in the ionic lattice.
Okay, so number one is you've got smaller ions. They always form stronger bonds because they're closer together. So there would be more attraction. Stronger ionic bonds are going to be formed. Any other factor? I mean, look at the ionic lattice. What other factor would determine whether the lattice is strong or weak?
How many electrons are being transferred?
I mean, the other one would be the charge. If you have an ionic lattice of, let's say, a magnesium oxide. I hope I find one. So let's compare these two. So over here you have Mg2 plus and O2 minus. On the other side you have Na plus 1 and F minus 1. So because of the greater charge, there would be a lot more attraction in MgO. Is that clear?
Yes, sir.
So the second point is greater charge on the ions, that automatically translates to stronger ionic bonds. So there are two factors that determine whether a lattice, an ionic compound, is going to be strong or weak. And the two can be combined into one thing, which is called charge density. लुबैना हाँ नहीं उससे मैसेज किया था नहीं हाँ ठीक है अच्छा charge density is directly proportional to charge of the ion and inversely proportional to the radius of the ion. ठीक है, is that clear?
Yes.
अच्छा, so strength of the lattice. So your lattice energy is going to be more exothermic or more not endothermic, but less exothermic, depending on how strong the lattice is. Sometimes the lattice could be very, very strong. For example, uh, I mean, can you name two very strong lattices, ionic lattices?
NaCl.
The NaCl is not a strong lattice. NaCl is a very weak lattice. You can easily break it into tinier particles by just crushing it in your hands. So examples of strong ionic lattice. Do you know of any ceramic material? I'll tell you one example is MgO. Okay, that's MgO and aluminum oxide. They are used as ceramics. I mean, there's SiO2 as well, but since it's not an ionic compound, so we're going to ignore that for a second. So these are known as ceramics. What are ceramics? Ceramics are substances that have really high, that are really strong, having they have high melting points. Plus, they're not soluble. They're not going to dissolve because they're so strong that it's very hard to dissolve them. And they are used as electrical insulators. Like for example, you've got I mean, look at MgO. Even though it has charged particles, but because the attraction is so strong that it's very, very hard to actually make the ions move. It's very hard to melt it. It's very hard to dissolve it. So it can be used as an electrical insulator. And these ceramics are used in places where there are extreme conditions. For example, there's a satellite, sorry, yes, a space shuttle that's entering the Earth's atmosphere. Then, or anything that's coming back to the Earth. So to absorb the impact of the atmosphere, you're going to put ceramic tiles around it uh, to protect it from the heat of re-entry. And then you've got furnaces. You make furnaces out of clay, SiO2, or magnesium oxide or aluminium oxide. So furnace linings, you use them for high voltage transmission because you want insulators. So you want some substance that could resist high voltages because when you have high voltages, uh, electrons get ripped out of atoms and molecules. Like even if it's a covalent molecule, even if you have a plastic cable, if the voltage is really, really high, uh, the high voltage is energy per charge. So because the particles would be so charged uh, that the covalent bonds and the ionic bonds, they would all get ripped apart. So you want something which has strong forces of attraction so that it doesn't let that happen. So magnesium oxide, aluminum oxide are good ceramic material. I mean, you can even ceramic high voltage transmission. Just 1 second. So I mean, a lot of your electrical, even your electrical extensions, etc., they have these white-colored substances inside, and these are made out of aluminum oxide. Plus, for high voltage transmission, I mean, pretty much all the, uh, I mean, if you, I mean, the holders of the electrical wires, they are made out of ceramics, etc. Okay, is this clear?
Yes.
So the main point, coming back to the main point, you've got stronger lattices, and you should know what the factors are for a strong lattice. The next thing we are going to talk about is, remember, lattice energy is very important because we're going to come back to it in a bit, and we're going to talk a lot about it because we would have to calculate the value of lattice energy. So right now we just did definitions and the factors that affect lattice energy. Next one is known as electron affinity. Do you know what electron affinity is? Lubena, any idea?
Mm, no.
अच्छा चलो ठीक है. No, you haven't studied, ठीक है? So which is why you probably shouldn't have it. You should have no idea actually. As electron affinity is, it's the opposite of ionization energy. So ionization energy was when you were trying to remove electrons from an atom. Here you're trying to gain electrons, so it's the energy released or absorbed when 1 mole of electrons are added to a gaseous atom. Are added to 1 mole of atoms in gaseous state. This could be ions as well. So forming 1 mole of gaseous minus one ions. Like for example, you've got oxygen atom, and it's trying to gain 1 electron to form oxygen minus one. ठीक है, is that clear?
Yes.
So this is known as electron affinity of the oxygen atom. I said the difference between ionization energies you talk about first and second and third and fourth. In electron affinity, you state electron affinities by talking about who's gaining electrons. So this is the electron affinity of the oxygen atom. I mean, this is not known as the first electron affinity. This is known as the electron affinity of the oxygen atom. If oxygen tries to gain another electron, so now it has gained 1 electron. If it tries to gain another electron, so it's going to form oxygen minus 2 gaseous ion. And this would be known as the electron affinity of the oxygen minus 1 ion. Okay, is this clear?
Yes.
And so on. So if oxygen decides to gain another electron, then that would be the electron affinity of the oxygen minus 2 ion. Now, electron affinities are usually only discussed or talked about for atoms that gain electrons. I mean, you're not going to talk about electron affinity of the sodium atom because it never actually gains electrons. So we're going to talk about electron affinities of non-metals that tend to gain electrons, and we're not going to talk about the electron affinity of the oxygen -2 ion because oxygen usually just gains 2 electrons. So you should know that, for example, nitrogen is going from gaseous state and gains 3 electrons, and it turns into N3 minus gaseous. So in terms of electron affinity, can you define what this is in terms of electron affinity? Any idea?
Energy released or absorbed when 1 mole of
No, what I'm saying is, okay, in terms of like this was electron affinity, like in the red, right? This was electron affinity of the oxygen atom, right? This was electron affinity of the oxygen -1 ion. What is this? I mean, it's electron affinity of what?
of nitrogen -2.
No, it's not. This is basically electron affinity because three things are happening over here. I mean, first, nitrogen gains electrons and turns into N-1 gaseous, right? Then N-1 gaseous, I mean, there's plus 1 electron, right? Then N-1 plus 1 electron, it gains electrons and it forms N-2, right? And then finally you have N-2 trying to gain an electron to form N-3, right? So every time it's trying to gain 1 electron. So your starting point is N over here, and you ended up over here N-3, right? This is what's happening in the reaction, right? Is that clear?
Yes.
So this is basically happening, what's happening over here. So this is basically electron affinity of N. So the enthalpy change of this reaction would be electron affinity of N plus the electron affinity of N-1 plus the electron affinity of N minus 2. Okay, so it's the sum of 3 electron affinities. So is this clear?
Yes, sir.
So remember, whatever process that we study later on, N would actually go from N to N3 minus, right? So you should be aware of the fact that this is 3 electron affinities. Similarly, oxygen would also be, I mean, your reactions, oxygen wouldn't go to O-1 first, it would directly go to O-2. So that would mean electron affinity of the oxygen atom plus the electron affinity of the oxygen -1 ion as well. ठीक है, ये clear है?
Yes, sir.
Now, a similar thing is, I mean, you've studied ionization energies. Let's also talk about ionization energies a bit. I mean, we know we've done the definition. Ionization energies is the energy that is needed it's the energy that is needed to remove one mole of electrons gaseous atoms to form one mole of gaseous -1 ions. So here's what ionization energy is. This is the first ionization energy. It's sodium losing an electron to form sodium that's plus one. Okay, is this clear?
Yeah.
Now, in this case, can you tell me I mean, this is the first ionization energy. How would you write the seventh ionization energy of sodium?
Na plus 6 gives us
Okay, so it's going to be Na plus 6.
Na plus 7 plus 1 electron.
Okay, so it loses the seventh electron and turns into Na plus 7 plus 1 electron. Okay. So, what about what is this? Al1 plus changing into Al3 plus and loses 2 electrons. How would you define that? In terms of first,
Ionize
yes.
the ionization energy of Al1 plus and Al2 plus.
The ionization energies are always in terms of first, second, and third.
First plus second plus third ionization.
So this one is equal to the second ionization energy plus the third ionization energy. ठीक है, so remember when you're given expressions like these, you should know how many energies are getting added up. Same with electron affinities. If you're given expressions like this, you should know how many electron affinities are getting added up. ठीक है, is this clear?
Yeah.
So, ionization energies are always endothermic. Like, for example, I mean, I wrote it's always energy that is needed, right? But electron affinities are both. It's energy released or absorbed. So, for example, look at oxygen. The two electron affinities. What do you think the first one is? Is it endothermic or exothermic? Just make a random guess.
Exo.
I said, so now, and look at nitrogen as well, right? Let's focus on nitrogen as well. Just a second, this is not moving. So let's focus on nitrogen as well. Do you think it becomes more difficult to gain electrons? Like, it's easier to gain the first electron and way more difficult to gain the third electron? Or does it become easier to gain electrons? Any idea?
It becomes more difficult.
It's going to become more difficult to gain electrons. The first one is always easy, and it's usually exothermic. Why? Because nitrogen is a neutral atom, and it gains an electron. It attracts an electron, gains it. But when it becomes a minus one ion, it doesn't really attract electrons anymore because it's a negative ion. Negative ions would repel other electrons, right? Is that clear?
Yeah.
So negative ions would repel other electrons, which is why, and if it becomes negative 2, then it becomes even more difficult. So it's going to turn endothermic at the second electron affinity, and it's going to become more endothermic as we move further down. Negative ions, they're going to repel electrons. So it's going to be very hard for them to actually gain electrons. So the rule is usually the first electron affinity is exo, or we can say the, I mean, since it's not first, second, and third, electron affinity of the atom is exo. And electron affinity of negative ions is endo. Okay, so it's because of repulsion, it becomes really difficult to actually gain electrons as you move further and further down the group. Okay, is this clear about electron affinity?
Yes.
So now, so we're done with ionization energies, we're done with electron affinity. We talked about what, so we talked about what, sorry. So we talked about what lattice energy was, and that was exothermic. We talked about enthalpy change of neutralization, which really doesn't, there was standard enthalpy change of combustion and formation. So we've done all that. What we haven't done is enthalpy of solution and hydration. But we're going to do that later on. In the next class, what we're going to talk about is there's going to be a Hess cycle, which is going to be known as the Born-Haber cycle. Okay, the other definitions can wait. So in the next class, we will be talking about the Born-Haber cycle. And this cycle is specifically for calculating lattice energy. You measure and you calculate lattice energy using this cycle, and the other thing about this is that uh, remember it's we'll also talk about the Hess law or the Hess cycle. It's kind of a Hess cycle which is given a specific name. Okay, so we'll do that in the next class. This is something that's more important. We just did definitions for now. Okay, so we're going to continue with this in the next class. ठीक है लुबैना?
Yeah, yes, sir.
चले ठीक है. चले ठीक है. Let's discuss this tomorrow then. चले. Okay then.
Allah.
Take care. Allah Hafiz.